welcome to this video about magnetic flux. So magnetic flux is basically how much of a magnetic field goes through a surface. So it is represented with this surface integral and magnetic field and this differential of area. So basically, the magnetic flux is on this side. The other side is its definition, but it's uppercase Greek letter phi, and on the other side, the B is the magnetic field, which is a vector field. It has a component for each direction, and it's dotted with the dA, the differential of the area of the surface. So imagine we have a surface in space, right? Let's put a little angle here, and the dA will be perpendicular to it. It's not perpendicular. It'll look kind of like this at a 90-degree angle, and it is the dA. And the magnetic field will just give the vector lines like this. They'll go through the surface. All right, and okay, so let's kind of write it another way. The magnetic flux, this magnetic flux equation we have here, and it's true that is true. It's a surface integral with two integrals. It can also be written as one integral. Like we'll just write it like that. Closed integral of B dotted with dA. So recall what a dot product is. It's a scalar product of two vectors, right? And usually it's written like this. So imagine we have vector A, right? We have A vector is, it has its first component in the x or I direction, A1 in the I direction, plus we have then our A2, the second component, in the J direction. Then in 3D space, the last one's the A3 component in the K direction. Then we have another vector B, which is just the same, but with B's components. It has B1 in the I direction, added to B2 in the J direction, B3 in the K direction. So a dot product between these two, between A and B, it usually multiplies all their components in their respective directions and adds them together. So it's a scalar, right? Just from multivariable calculus and vector analysis. But recall there's also a geometric interpretation of the dot product, and that is that A dotted with B equals the magnitude of A multiplied by the magnitude of B. And remember, there's an angle between vectors. We multiply by that cosine of that angle, right? And the magnitude's just how long the vector is, and it comes from the Pythagorean theorem. So the magnitude of something is the C, we would be able to call it, but instead of being like a squared plus b squared plus c squared. It's the magnitude of the vectors that are the a plus b, but it's in 3 dimensions. So the c, or our magnitude, is the square root of all its components squared. So in this, in magnetic flux, it can be rewritten using the geometric interpretation instead, which is also scalar because then it's multiplying magnitudes and a cosine. So that turns into the let's just write the dot product of B and dA. We don't know anything yet about the angle between these two because it's specific to each situation. So, but what we know is that dA is perpendicular to the surface, right? But that doesn't give us much yet, so let's just write it as the magnitude of B times magnitude of dA times cosine of the angle between them. But really, the magnitude of B, just write it as B without an arrow, and magnitude of dA as dA without an arrow. So then the over here, the definition of the magnetic flux is just the integral of B dA cosine theta. The integral cancels the differential, so the flux is the magnitude of the magnetic field times the area of the surface times cosine of the angle between them. There we have the, just using algebra, the definition of the magnetic flux. Just multiply all these things you know of the problem. So for this example, we know that we have a vertical surface here, and the angle area vector perpendicular to that is completely horizontal. The dA or a vector will have the same direction, just different magnitudes. So the we know that the magnetic field is also going in that same direction. Magnetic vector field is also going perpendicular to the surface in the same direction as the area vector to the right. So theta is 0. A cosine of 0 is 1. So the magnetic flux is just equal to BA. So what about this one? See, the surface is inclined a little bit, so that'll also change the direction of the area vector. So here we can see that now they form an angle with the magnetic field vectors and the perpendicular area vector that's perpendicular to the surface. Remember that area vector is just here the position doesn't really matter. Well, yeah, some do intersect at 45 degrees, but at any place they would intersect at 45 degrees. So since we know the angle between them, it's 45 degrees, so the cosine of that is just square root of 2 over 2. Both sine and cosine of 45 degrees are square root of 2 over 2. So the magnetic flux is equal to AB square root of 2 over 2, or 1 over square root of 2 if it's not rationalized. Lastly, let's look at this one at the bottom. We can see that this one's kind of different. The surface is flat on the ground, it's horizontal, and its perpendicular area vector is going directly up. So if the magnetic field vectors are still going horizontally to the right, then they're also forming this perpendicular angle between the dA vector and the magnetic vector field. So theta equals 90 degrees, and cosine of that's just 0. So there is no magnetic flux. I hope this video helped. Thank you for watching.